Soon it will eventually it will succeed, I would imagine, right? Okay. Okay, so today we are back to this exciting topic of managing processes virtual memory. So it gets quite involved. It took me some time to understand how it works in Linux, and it took me like I had to go through multiple sources. So, but hopefully, after listening to me for a little bit, you will be able to it will be much easier for you yourself to understand what's going on, and maybe hopefully if you ever have to come back, you will be able to quickly reconstruct the sequence of events. This it's trying to get this camera working. Is it any better? Maybe, but potentially not better at all. Okay, so just a quick reminder, right? So each process has its own address space, right? So we talked about it, so it's not a big surprise. It's exactly the same as in x86. So the major difference in Linux is a couple of things which they need to support as a real operating system. So more specifically, what they do is that they say, look, first of all, we want to support a bunch of shared libraries, right? So x86 didn't do anything like that. Do you remember that in x86, everything was linked statically? I mean, x86 did have libraries, right? libc, stuff like that. They didn't call it libc, they called it something like utils or something. They had a memory allocator. It was all compiled as just object files and just linked directly, statically in a single, in the actual binary of the program, right? So in Linux, and if you remember my regular OS class, I was explaining it that typically when the process starts, it just loads a tiny little stub in memory. And this tiny little stub essentially is called a linker and linker loader. And this linker loader actually is responsible for assembling the program in the address space, right? So because, for example, if you say you link a tiny hello world program like main, it will rely on a bunch of shared libraries, which implement libc, which, for example, provides a layer system calls to call back into the kernel. Things like printf, stuff like that, right? Even to like do hello world, we need a printf. And all of it is in Linux, it's all shared libraries, right? Do we remember shared libraries at all or not? Yeah, and so these linkers are loaded, and then shared libraries are, when the linker is loaded, the linker itself says, okay, I can allocate more space in the address space. And what is the address space? So the address space is everything on this diagram. It starts from 0, goes to this 2 to the power 48, right? So this is all virtual address space of a process, right? Everything above is address space which belongs to the kernel, and it's not typically, but is not accessible to the user, right? Besides maybe like 1 or 2 pages which implement a trampoline for invoking system calls, right? And so essentially when the linker says, okay, I need to resolve all the dependencies needed to run this program, it will be allocating regions of this virtual address space, right? And also it will like obviously allocate some regions to have the actual text in it, read-only data sections of the program itself, writable data and BSS, and so on, right? So obviously what you need to do, your kernel, the moment you say, look, remember how x86 was managing the address space? It was very, very simple. So in x86, the address space, user part of the address space was running from 0 to 2 gigabytes, right? And everything was linked statically to executed address 0. So essentially like the text and then data section of a program were allocated, and the loader, the loader itself was part of the kernel. And the loader was, when the program was loaded from disk, first reads the out header, then reads the program, what is it, program header table, the name exactly, right? Essentially just says, okay, look, those are the parts of the program which will be loaded in memory, right? And the address space, remember each process in x86 was represented by a probe data structure, and it has a size field, right? And the size was originally equal to 0. And as the loader was loading the address space, the size was growing along with the stuff which was loaded in the address space, right? And that was it, right? And then the kernel was allocating a guard page and a page for the stack, right? And after that, the size was pointing right here. And when the program starts, for example, when you execute something like malloc inside x86 program, it starts using set bracket sbrk system call to grow the heap, right? You remember this? So everything was super duper simple. Actually, allocation is simply a fact of checking whether the size already hit the 2 GB mark, and if it didn't, like essentially extended by requested amount rounding up to the pages, right? And essentially allocating those pages eagerly on the eagerly as like in the same system call, right? Remember this? Very, very simple. And okay, cool. This can run like this, but it's not super efficient, right? And the problem is there are multiple different problems, right? But most obviously, this architecture does not allow you to support shared libraries easily, and does not allow you to support something what is called copy and write when you fork. In x86, the entire address space of the program was copied eagerly on fork, right? And in Linux, it's not done, and no operating system does it, right? Because it's just too expensive. Okay, so in Linux, this address space is allocated differently, right? So it's also managed by an allocator, which keeps track of available virtual address space. So essentially, when you say, look, I want to allocate some space for yet another library, you have to find a gap which is still available and say, look, use it, right? And we talked about it. And we also talked about the layout of the 64-bit address space. And it's again, it comes from this document online, which is official part of the Linux kernel. And this specific layout represents the layout of the address space, which support 5 levels of page tables, right? So, and specifically, if you look here, so user virtual memory is 64 petabytes. That's quite a lot, right? So we will not run out of this address space in foreseeable future. The kernel address space starts here. They use the negative notation, but it's minus 64 petabytes. And essentially this is the address, right? And so on and so on, right? And you can, like, if you really carefully read through it, it will make some sense to you. So for example, remember we talked about vmalloc. So, and I think the vmalloc region is specifically here. So that when the kernel, instead of going to a body or a kmalloc and tries to allocate a large chunk of memory, which is assembled from multiple physical pages, this is where those pages show up, and this is where the region will be mapped in the kernel, right? And so again, like I don't want to spend a lot of time because this is the kernel part of the address space and it's not as interesting. And the user part, we kind of like, we'll also make it, we discussed a little bit of this detour that in case your address space is small, then you may run out of heap, because if you reserve a specific, if you say, look, I only reserve so much space for the heap, then or rather this, I guess, then I may run out of it, right? So it's not okay. And so they for smaller spaces, the way it works is that the heap and the mmap area are growing towards each other, and the stack has a static reservation, right? But that's okay. That's kind of setting the stage for what's going on. The question is the question today is how the kernel can manage the user part of the address space. And at a high level, remember, we talked about it a little bit. These are the data structures which are involved, right? So each thread and a process in the system, let's call it a thread, is represented in a kernel with a task struct, right? This task struct has a pointer to mm_struct. And this mm_struct represents an address space. So for example, if you have multiple threads running in the same process, they will share the same struct, right? So because they don't need to have individual structs. And struct itself has a pointer to the page table, right? To the root of the page table. But what's more interesting for us today is it has this pointer mmap to a list of virtual memory areas, VMAs, virtual memory area, right? And each of these virtual memory area, VM area struct, represents a region in the user part of the address space, right? I briefly touched on the fact that VM alloc area is also managed in a similar manner with slightly different data structure, slightly more simple, but conceptually similar, right? And essentially, okay, so if in this case, this is the address space of the process, like in this example, we have 3 different regions. So the kernel will create 3 different VM areas, right? Agree? So not super hard. So far, so good, right? So, and obviously, the question is what do we really need from these data structures? And okay, let me hide this slide for a second. So what are those operations which we need to perform? Let's just think through, try to guess how we can implement that and things. So what do we need to do? Who can tell me? No, what happens when we want to load a new shared library?
We increase the virtual memory area for shared libraries, allocating extra space for them.
I think actually what will happen is that you will, if you want to load a new shared library, you will actually allocate a new VM area. And the reason for that is each VM area, which is backed by a file, has a connection to that file. Because later on, you have to decide what to do. If you, for example, swap something out and release a page and encounter a page fault, you have to resolve where you are in the file, right? And there will be a pointer I will explain in a second, right? But okay, so at a high point, at a high level, yes, what you were saying, but I will make it slightly more involved. At some point, if Linux loads hundreds of those different areas, and there is a way to take a look at what is actually loaded, you need to figure out the free space. So this is somewhat similar to the allocation, right? Similar to how we are allocating pages, right? With let's say body, we need to allocate a free region. So what kind of data structure we can use for that? How is it a tree? Yeah. So, the most trivial approach is to use a linked list, and this is what kernel is doing as well. And essentially, you can say, look, what the kernel is doing, they maintain a linked list of these virtual memory areas, and they actually sorted by the starting address, which means that you can at some point say, look, I'm gonna scan through the list, and I will try to search for the gap and figure out the gap, right? I actually take it back because I'm not 100% sure that this is what kernel is doing. Because as you said, they also use a tree. And they use something what is called a red-black tree. And this red-black tree sorts the virtual memory areas. And I think it's much easier to find a gap by essentially traversing the tree. But I'm not 100% sure how it's done. You have a question?
So here the VM start, VM end, that's the virtual address.
Correct. Because you have, remember in a previous slide, we had something like from 0 to 2 to the power 48, right? Now this power is even bigger than 48. So it's like out of 64 bit of addresses, like this part 2 to the power 48.
So -1.
Yeah, -1. Is used. And this is the space which you are like trying to allocate. But you can say like, you may ask a question, okay, how many shared libraries have a load in this address space? And you say, wow, maybe 10, maybe 100 max, right? So it doesn't seem like a hard problem. But also modern programs use something like mmap to allocate what is called regions of memory, which are not backed up by files. Those regions are called anonymous regions. And there are two kinds of those regions. Ones are private to a process and ones are shared, right? And private can be used for heap. For example, instead of using set bracket system call, you can do an mmap, and out of that mmap area, do allocations with malloc, right? Or you can do a shared region and it's essentially shared with another process, establishing a region of shared memory for communication between processes. A much faster way, as we discussed before, compared to something like Python, for example, right? So okay, we understand. So one operation is allocation, right? So we need to allocate regions. Free regions, right? What's next? What else do we have to handle?
Update the page table.
Well, why is that? On what operation you need to update the page table?
Because if we need to load the shell library, we need actually physical memory space to hold that.
Right. So you need to be able, like the moment you created like the virtual memory area struct, which represents a shared library, and I will explain the data structures which sit underneath, you will be allocating pages from very similar way from body, and you will be backing up those this area with pages and like loading them from disk, right? There is, however, a trick which the Linux kernel is doing.
Lazy.
Exactly. So it never allocates. I mean, I cannot say never, but almost never, and I'm not sure if ever, but maybe. It almost always says, okay, I will allocate the virtual memory area, and I will do nothing in terms of allocating pages. What leads us to the following idea that the moment you start reading from that page, you encounter a page fault. At this point, the kernel has to, like, if you have an address, like a physical address, on which you have a fault, you have to quickly look up to which virtual memory this address belongs, right? So your operation is essentially a lookup to understand out of this list, maybe 100 elements, which virtual memory backs up this physical address, or maybe none, and then it's a SEC fault, right? And if there is one, then like follow the data structures and read something from file, right? So we need a way to efficiently look up those virtual memory areas. And I will just like in a second explain briefly, but they are maintained as the red leg tree, and the tree is balanced, so look up as log n, and so that's how it's implemented with a tree essentially, not just a linked list. Okay, cool. So we have a lookup, allocation, lookup. We also need to support something what is called, and we can call it a page in of a page. Page in, meaning that you take a page and like bring it into memory from disk or swap device. But you also need to make sure that you support something what is called a page out. And page out of a page or swapping of a page is an idea that, you know, if you touch the page maybe once when you load the program in memory, and then it sits there idle and is never accessed, and it can happen, the kernel itself will identify this fact and will try to say, look, we will take this page to a swapping area on this, or if it was read-only on file and was never modified, we'll just simply discard it, right? So for that, we need to do a couple of things. So do we understand how it works, how paging works? I think everyone at a high level, we all understand how it may work, right? The devil is in the details, right? Because Because when you essentially try to identify the victim pages, you create some stats about how often the page is accessed and stuff like that, and that's fine. But imagine you found a candidate page and you say, look, this page doesn't seem that it's accessed very, very often. So it sits there idle. So it's a good candidate for a swap out. It can be mapped by hundreds of programs in the system. Multiple examples, like there are two different like kind of lines of how the page can be shared. And one is from a parent to a child, when you're essentially forking, you do a fork. And I will explain this idea later, but essentially the memory is not really copied immediately, right? But the kernel just creates a link between the child and the parent, and essentially, eventually, a parent might say, "Look, I touched the same page," but the page might be mapped into multiple address spaces, and you have to figure out all the address spaces in which the page is mapped. Why is that? Because if you want to take this page down, you have to update every page table of every process, right? And to essentially mark it as like unmapped or invalid, right? Not present. And that's an operation which requires you to essentially be able to resolve from a single page, resolve all address spaces.
Reverse the map.
Exactly. No, I'm glad that you know these words. So it's pretty advanced because in my x86 class, I never used the words reverse mapping. But yes, it's really a reverse mapping. So you essentially saying, okay, you need to understand how the pages are reverse mapped to processes, right? To essentially those structs which are sitting here. And okay, and it's done in a kernel. It's done differently for different kinds of pages. For anonymous pages, they take one way, and for the pages backed up by files, they construct a more sophisticated data structure, which I will explain today. Okay, cool. And obviously, we also need to support something what I mentioned, this copy and write. So essentially, when a parent forks, instead of like doing a copy of the address space, we need to maintain links between children and parents, right? And I will not explain copy and write right now, but I will like come back to it and explain like some data structures, right? So any questions about this? High-level overview of what we want to do with the address space. And again, the question is, I will not ask you to do this, but imagine someone says, okay, we want to quickly build a startup. We will use x86 as a starting code base. Everything is fine, but we want to support shared libraries first. We don't have that much memory, but our programs are really Apache and stuff like that. And second, maybe we want to support like open write and things like that. So this is what you're looking at if you want to kind of bring a similar data structures or similar infrastructure in x86 kernel. And the two kernels, which I know, FreeBSD and Linux, they do this conceptually in a similar manner. I don't know how Windows does it or macOS. Well, the macOS sits on top of FreeBSD, so maybe it does it in a similar manner as FreeBSD. Okay, cool. So this is the operations. So right, they find available virtual addresses to allocate a new VM area. Page in case of a page fault, to essentially like quickly look up the VM area and figure out whether the page fault is legit and where the page is coming from a file or just from a swap device or just was never allocated, so which is called demand paging. Or page out a page to essentially identify all idle pages and make sure that you can unmap them from all other spaces, and support for copy and write, right? Okay, let's take a look at how it's implemented. So I already said that, okay, task struct, this one represents a process or a thread, and the threads share the same struct, right? Because they are just operating the same address space. As I said, struct has a page pointer to the page table, and if we take a look, and this listing does not correspond to the recent kernel, it comes from this Gorman book on memory management, which I recommended for the homework as well, because sometimes he writes, his writing is a little cleaner. But essentially what we have here, this struct has a pointer which says, okay, this is a list of all VM areas, right? The same VM areas are maintained as a red black tree, and I will explain in a second why. So this is the root of the red black tree as well. This is the last when you essentially try to locate a virtual memory area in a red black tree, for example, you search through the tree, you find it, you remember it in this pointer, mmap cache essentially is the last one which we figured out. We assume that we will need it again, and so we keep it around. We'll always check it first. Root to the page table, and more or less kind of predictable attributes, like where the start of the code section, end of the code section of the program, start of the data section, end of the data section, start of the heap, end of the heap, start of the stack, start of the arguments which are passed from the from the exec system call, end of the arguments, and so on, right? So nothing super unpredictable, right? But the most important fields which we care about is this linked list and a red black tree. And moreover, if I understand correctly, you look at the most recent, like this linked list existed in version 2.6, it's described in the book, but in the most recent kernel, version 6, I think they gave up and there is no linked list anymore. I'm not exactly sure which operations are affected, but I think they said, okay, red black tree is just good enough for everything. Okay, cool. And inside this VM area struct itself, what's important here is a backward pointer to the address space itself, the start and end of the virtual memory area, this is the field which allows the kernel to maintain the to put it on a linked list sorted by the addresses, right? And similar, there is a node to be maintained on a red black tree, setting protection attributes and stuff like that, right? So okay, so and if I like click here, and I hope it will open. Let's see. Does it? Hopefully it will. Let me click maybe here. I just wanted to make sure that we go back to the kernel source code for the most recent kernel. Yeah, man, like, where is it? Really not. I'm not sure how to click on the link still, but we can do it here. So if we go here, we'll find it again, one of the most recent versions. So VM area struct, like I was saying, end and start addresses. Back pointer to the address space will belong to protection attributes. And where is my red black tree? The red black tree is here, stuff like that, right? And so essentially just wanted to make sure that we understand that this is like not a fake data structure existing, right? Okay, let's go back to the slide deck. Just keep working through it. We share again. Okay, so and if we care about what's going on, we have to essentially take a look at this diagram, which represents dependencies between the data structures. And in my wonderful homework assignment, I want you to draw something similar. I'm not saying that I mean, you may or may not be as detailed as this one, because it's hard to understand everything. But at least something similar. Make sure, because the way it's much easier to understand what's going on when you have this diagram, which essentially this right here, for example, what it lists here a type. For example, here struct, struct. And this is a pointer mmap, which points to the VM area struct. VM next points to the next area struct, and so on. VM file field points to a file, right? So what's important to understand here is the following. So at some point, remember I said that there will be two kinds of memory areas. Ones are anonymous, meaning that they are not backed by any storage. So essentially, you just simply either allocate memory, and then when it's deallocated, it's gone. It's not persistent on disk, or file mapped. And a file mapped, essentially, you also do an allocation through the same interface, like mmap, but this area is coming from a file, right? And so, meaning that when you write into a page, at some point it has to be flushed back to disk, right? And so there is enough data structures here. So this VM area struct will have a pointer to a file data structure, which will have a pointer to a struct directory entry, then later to the struct inode. And this inode will point to something what is called a struct address space. This address space will have AOPS, like a pointer for a collection of function pointers, which implement the interface of this address space. And essentially those functions which will allow you to write like data back to disk. And like different file systems can implement those functions differently. So that's why it's in there is this polymorphism there, right? But that's important to understand, right? Okay, cool. So then in this these VM operations also can be overloaded. It's a collection of function pointers, and those essentially allow you to specify what happens when you open and close the VM area. And open and close are not used very frequently. They are just used in some esoteric corner cases. But what's important is this no page handler. And this one essentially handles a page fault. And there might be, again, different implementations, but typically like implementation of a no page will locate the page on the page in the swap area, essentially. I mean, either it's already on disk in the swapping area, or it's still in a buffer cache, and then, okay, maybe it can be like remapped here back again, right? So those VM operations implement like essentially handling of a page fault. And so essentially what I wanted to highlight here, that from this pointer, from a file pointer, VM underscore file pointer, you will eventually lead to an address space, and the address space will know how to essentially flush the files on disk, right? And like you can also click here to like make sure that how this is implemented in the modern kernel. Okay, now back to these operations, which I was advertising. So the question is, how will we implement them? So we need to implement the first one is to find available virtual addresses, right? So for example, when the kernel wants to map something new, like either load a shared library, or memory map a file, or just create a anonymous region, which will just provide memory for the malloc allocator. So essentially, it boils down to this get unmapped area function, which again can be overloaded in the kernel by different specific architectures. So for example, some of the architectures can say, look, we do not allow all the mappings are fixed. For example, you cannot really change the layout of the address space. Or there might be some other specific considerations. So for example, you can implement randomization there, and essentially on purpose, like make sure that you're picking the addresses randomly to make sure that it's harder to attack the kernel, right? But at a high level, so essentially, at least in this, it uses this VM next pointer, and essentially iterates through the address space to figure out the next available region, right? And I said that in the past, the linked list was used. Right now, I think the iterator is actually using the red black tree. Let me just go here, figure out just real quick back to the slide deck, just a quick. I mean, I was expecting that I can click on it, but I somehow cannot. So again, if we go here, so this like after like going through a chain of invocations, you land on this unmapped area. And what it does is that it has an iterator here, which gives them the lowest address, and like it's not a loop, or you're not sharing. Okay. Why is that? Because this thing. Okay, got it. No, I'm sharing it actually, but so it's visible on pop-up. It's the slideshow like this. No, pause doesn't work. And slideshow. So what happened here, I landed on this function and mapped area. What it does here, it just like implements an iterator, I believe over a red black tree, which guessing returns you the lowest address, right? And then it will essentially try to figure out a gap. And if it matches certain characteristics, then you will return a gap to the caller. If not, you will go to retry and to the next version, to the next round of iteration, right? So at a high level, okay, not complicated, but probably the details are involved. And I cannot read all of it, but I mean, we can take a look at what the iterator is doing, but we may as well get stuck there. Like, what is mass index? Who knows? But okay, good luck to you. You can read. No, but okay, I'm also kind of scared, but at some point there will be okay. Okay, good question. So, yeah. So again, so all the programming classes kind of teach you not to ever use a goto, but the kernel does use a bunch of gotos. I think, I mean, the kernel developers are kind of very, very skillful and they have a specific programming discipline. I'm not an expert, but arguably this increases the readability of the code. You can implement it as like a while, infinite while loop, and then say continue, right? But does it really change or improves the readability of your code? Not exactly sure. For any other tool like static analysis tool, it doesn't really matter because the same while loop will be implemented as a jump to somewhere eventually over that. So the kernel, if you take a look, gotos are frequently used in those retry statements, and I will try to find you one which essentially does some error handling. So kind of, so again, error handling, especially if you have multiple like conditions which you have to handle, gets pretty involved, right? And so, for example, this one is a label which clearly identifies the success condition. Here, this one is a fail. So and they do it quite often, but probably not much besides that. So in general, you will find that the kernel code is reasonably cleanly written, although it took them forever. Besides maybe device drivers, which is committed by some third-party developers and stuff like that. So, any other questions? But yeah, don't get. Again, I like. Again, spending so many years doing this, I like their choice of names as well, if we want to comment on that. So it's not like any specific, everything is lowercase and they use underscores, but you can often guess from a name what it means, and often the names are reasonably chosen to be short as well. So this DNA here in stands for memory now. Adder, obviously, like you can guess their semantic meaning from those, and they are very, 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 very short. So don't forget that it's 24 million lines of code today. So it's a huge code base. The fact that you can understand parts of it is also pretty crazy, and it's reasonably understandable, to be honest. I mean, to be honest, but you can. It's also easy to make a mistake as well. Okay, go back to the slide deck. Okay, cool. So we figured out how to okay, let me reshare. You have to switch between the screens. We're sharing this. How to find implement a find operation. So the next one, essentially how to bring a page on a page fault, right? So again, as I was saying, what's involved is that a quick search through the red black tree, which essentially allows you to quickly understand whether the address is a legal address, either was not allocated and it's in on-demand allocation of memory, or maybe it's like was taken to disk as part of the swap out process, right? Or maybe it's copy and write and stuff like that. So, and at a high level, what's involved in demand paging, to essentially, if the process tries to access a part of the address space, and the page table entry says not present, for example, page fold is triggered, a low level, very kind of similar to x86, but more involved, and we can talk about it. I don't know if it makes sense, but let's see. Kind of like exception handling, trampolines and stuff like that are similar to x86, a little bit more involved, but essentially same idea. At some point you get to the exception handler, and the exception handler says, okay, look, I will, like, there are multiple paths through the kernel, right? And in a second, I will explain the reasons which can trigger a page fault, but essentially at a high level, everything boils down to understand whether the region was mapped, was allocated previously, and what needs to be done to make sure to either bring the page back from disk, from backing store, or like essentially just allocate it, right? And the reasons for page faults, like Linux essentially distinguish this major and minor page faults. And major ones are the you have to go to disk and read it from disk, and a minor one you have to just resolve in memory. So for example, you have your VMA is valid, right? So it was allocated, but the page not allocated. So it's demand paging. So what happens is that it's a minor page fault, and you simply allocate a page frame from the body allocator and map it into the address space, right? For example, region not valid, but is next to an expandable region like a stack. So for example, the stack has regionally a size, and then it keeps growing, and at some point it says, okay, I need the next page because I grew out of the originally allocated region. And what the kernel will do, it says, okay, the address is invalid because it's not in the EML, in this virtual memory area, but some virtual memory areas are allowed, they're expandable. So you can expand them specifically this stack, right? And then you say, look, can you expand the virtual memory area? Yes, you can. And then we'll allocate an extra page for the stack, right? So it makes sense. For example, page swapped out, but present in swap cache. So again, this is the case. So the swap cache today is really a buffer cache. And but the idea is that somehow the page, you are trying to take the page down to disk, but it's still present in a cache, or maybe someone brought it back and it was previously unmapped from your address space and later on was brought back because someone already paged on it, right? And this, you again just reestablish the page in the process page tables and drop the reference to the swap cache. So essentially just map the page in. If it's really in a backing storage, then it's called a major page fault. And then you go and read it from disk. Remember this address space separations and stuff like that, right? For example, page is written, but the page is accessed on write, but the page was marked as read-only. So it's again a minor page fault. And the most common reason for that is that you're really trying to implement this copy on write. So when you clone the address space, essentially a child forks from a parent, or a parent forks and creates a new child, you say, look, eventually you all will have private address spaces. But for now, we'll not copy anything, but instead mark everything as read-only. And when either child or a parent writes in a page, in a read-only, in a writable page, but which is marked as read-only, a page fault is triggered. And at this point, the page fault handler will create a second copy, because at this point, child and parent will be diverging, right? Someone will have 0, one will have 1 at this point in the page, and there will be 2 physical copies of a page. But it's quite clever, this copy and write thing, right? So, and an interesting case, of course, how you maintain those chains of forking when the child forks multiple times, right? So that we have to discuss. But again, it's a minor page fault. But of course, there can be a real error. So for example, you're trying to access an address which is outside of your virtual memory areas, right? So it was never allocated. And this is exactly like you say, oh, there is a bug in my program. And this is where you receive your stack fault error message on your screen, right? This is when essentially the system will kill the process. There's also like a case where the fault can be happening in the kernel part of the other space. Typically, it's related to this vmalloc area, because vmalloc is also lazily managed, right? So remember, it's similar to virtual memory areas. there will be a separate similar data structure, and the backend memory is never allocated eagerly. But there are some other reasons as well, so it gets a little bit more involved. Or like, for example, like this is probably related to copy from user, but I like the description is a little vague, so I'm not really sure what's going on here, but also a bug. So we will maybe go through like more of this page fault handling, but at some point it's not as interesting. As long as you understand the major reasons, you will be fine, right? So again, a lot is involved at the lowest level, at the low level, and but at the high level, it's reasonably simple. The reason I'm spending time on this, right? So because when we go to other, I mean, in general, the reason I'm spending time on Linux, there are two reasons. One, to give you some exposure to how the full featured kernel looks like. But second is to understand what needs to be implemented for a full featured kernel. And if you want to change architecture of the kernel to implement, for example, like a library operating system, or implement like something like a hypervisor or exokernel or something like that, or a microkernel, the question is like, you always will have to answer those questions. What happens to a page fault? Or who manages memory and how? Is there a copy and write? Is there a memory sharing at all? And we'll be coming back to this, like every time we'll be talking about an alternative operating system organization, we'll be thinking in terms of, okay, what happens to virtual memory? Because somehow this virtual memory management is, I mean, probably the most complicated part of the kernel, and second, like, is central to the entire thing. Okay, cool. So we understand what happens on a page fault, right? As I was saying, so there is this red-black tree, which is like from task struct, use to identify struct, which represents your address space. This one has a root of the red-black tree, and so essentially you just descend in this red-black tree, figuring out the virtual memory area. This is the one. And then you say, okay, which one is that, anonymous or file mapped? And based on that, you decide what to do, right? So essentially, and at a high level, you are kind of like your diagram boils down to this, but we kind of already discussed it. So you say, is it a kernel user address? If it's a kernel, are you in kernel mode altogether? If no, immediately a segmentation fault because user cannot access kernel's memory. If yes, there is this idea that you can synchronize with the reference page table. So like when the kernel creates this, for example, virtual memory allocations in the kernel, which we map, right? It does not update the page tables of all processes, but instead it updates one, which they call a reference page table. Again, I have to take a look more deeper at how it works, but essentially it can happen that you just have a stale, that your copy is not updated and you have to update it, right? But I have to come back and like clarify how it works. But if you were in a user mode, you check, you go through this red-black tree, resolve into VMA, asking a question, if mapping does not exist, then it's a seg fault. If it does exist, do you have sufficient privileges? If yes, then it's probably something like demand paging or a swapping issue because it was taken to disk, or a copy and write. So essentially those three major reasons, right? And if you don't have sufficient privileges, for example, trying to write a read-only, a page which is mapped read-only, and for example, like text sections of libraries and your program will be mapped as read-only, you probably you're under attack. And so at this point, it's a seg fault, right? So this is clear? All good? Okay, cool. Then and if suddenly we are not an anonymous region, right? So this VM area struct is really backed by a file. You eventually will go to like through a collection of these pointers, you will reach this address space data structure, and this address space data structure will provide you these functions which will know how to bring the page back from disk. Yeah, and it will be from a file, right? So, and we will come back to a swap. So we'll take a look at the organization of a swap device. I don't really know how essentially whether this swap is handled here or through these operations. So it may be different, right? Okay, so now the question final operations is that we want to take page down to disk. So it's a little bit unusual because you think, okay, we already talked about so many data structures. What else can happen? Apparently something can happen, which is not super ideal. So our red-black tree is sufficient to essentially look up from a floating address into a virtual memory area, right? But if we want to take a page out, so essentially we want to say, look, we identified a page somehow. I mean, okay, if I ask you a question, so how do you monitor activity of a page? How do you know whether it's a cold page or a hot page? Whether it's a working set of a cold process or an idle page?
Time.
What is the machinery?
Sorry.
Machinery, what is the hardware? What are the hardware primitives which you are using?
Oh, as I know, the hardware, when you access a page, you will access the active bit.
Correct. So essentially, in a page table, I only draw like a 32 bits or 2-level page table. There will be a collection of bits here. And every time when you do like a load or a store operation, read or write from a page, this access bit is set, right?
Yeah.
And there are 2 bits. One is access, one is dirty. And the dirty is set when you do a store into a page. This allows you to modify. And so if you have some kind of a thread in a kernel, by the way, kernel can run threads as well. They never exit into user level. They just run in the kernel in Linux. It will just scan the page tables and figure out, okay, collect information about access bits and says, okay, this I've seen it was accessed recently, and we will maintain some kind of a list recently used list. And at some point say, look, this page was not used for a while. At this point, you say, look, I want this page to be unmapped. So if you have this pointer, right, you want to say, look, the present bit here, which is P, has to be set to 0, right? To say, look, this page is ever I don't know how exactly I can do, but this is the most obvious way to do it. Like you say, the present bit is not set, right? And so at some point, this page can be given back to the body, right? Allocator. The body can use it for something else, right? Agree with this? But of course, we need to figure out, as I was saying, there is another page table which also maps the same page. So it's a different CR3 here. And we need to figure out, going from a page, we need to figure out all the page table entries which point to this page, right? Agree? And so we somehow need to maintain this information, right? And what's the most obvious way to do it? The trivial way, if I assign homework, how would we do it? To keep information about all the page table entries which map a given page. And what, Stefan? Fixed size array. Why fixed size array? Let's do a linked list, right? So you can say, look, I will somehow maintain a linked list of I don't know, last level pages or even a page table. Man, it's not even last level pages. What if you mapped it twice? You're so crazy, right? So you need to really maintain a list. You understand that there might be multiple entries in multiple leaves of the page tables, which can map the same page, right? It's all legal, probably not super frequent in practice. But a linked list of these page table entries is a meaningful approach, right? I mean, the most crazy approach, which I forget who was suggesting last time, says, okay, let's scan all the page tables. Why not? And it was done. So I think up to the version 2.4, there was no infrastructure to resolve this problem. The only way was to essentially scan, right? And that's, I mean, works if you really run some embedded system with 5, 10, 11 processes, right? But on a server or desktop grade machine or a laptop, it doesn't work. Okay, so linked list is doable, but it's just too much information, right? Because those entries can be numerous and the pages are cloned frequently. What they do instead, again, I mentioned that they do two different approaches. One for anonymous pages, which are not backed by any files, and one for file mapped pages, two different approaches. For anonymous pages, they almost do a linked list, but instead of like maintaining a linked list of page table entries, they maintain a list of virtual memory areas in which this page shows up. And this allows you to kind of answer the same question with a little bit like you have to scan this list, but you're going from a page to this list and you scan and figure out, because from BNA you go to the MM data structure, right? And from MM you already know the address of the mapping, so because it has a virtual memory address, right? And then you walk the page table and you land on this, you land on the entry, right? And you can change the present bit, right? So this idea is clear, right? So like it's almost like a linked list, but just slightly up, not linked list of entries, but linked list of memory areas. And more specifically, what's going on here is like for anonymous pages, right? What's happening is, first of all, each page maintains a map count. So remember the page struct page, remember that array which I was saying, like metadata going from body, from the allocation, from virtual memory address to a physical memory address, from physical memory address to an entry in a page array, and an entry in a page array is this page data structure. And each page data structure will have this map count argument. So first of all, it will tell you whether it was ever shared or not, maybe not. And you don't have to do anything. For lookups, nothing, you just unmap it, right? But if the counter is like, I think it's non-zero and positive, then you have to start looking up. And so what they do, it's called reverse mapping for anonymous pages, right? So what you do here is that they do this trick. So again, in this struct page, there will be a mapping field, right? And this mapping field can have two different meanings depending on the lowest bit of this. And the trick, they say that mapping, essentially, there is a certain argument why all the virtual memory areas are something aligned. And so that's why the lowest bits are always zeros. That's why they are available to make them contain some flags, right? And depending on the value of this flag, this field mapping itself can either point to an address space or to a non-VMA object, right? Again, the reason why they're doing this, and you may ask yourself a question, okay, like why, okay, who can guess? Who can guess? Why is this complexity? Like trying to squeeze bits into lowest, trying to squeeze flags into lowest bits of addresses, overloading a pointer. A normal person would probably write something like a union here instead of, it's already a union. One would say maybe it's cleaner to write an on VMA pointer. What's the reason here? Safe space, exactly, because remember this page array has an entry for every page in the system. So if you have a lot of pages, like terabytes, like imagine you have a server with 64 gigabytes, or today you can, Flux has a machine with 1 terabyte of memory, which is needed sometimes. So they do those tricks. I'm not exactly sure why they haven't written a union or a struct and DNA here, I'm not sure. But essentially the same idea, right? But okay, to save space, it just, the reason I'm explaining it, that again, unless you know this little detail, it will take you forever. Like it's impossible to read the source code. People who wrote those books, at some point, yes, it's very well documented. So if you know how to comprehend this kind of moment, you will figure it out, but it's still hard. It was hard for me as well. And so, okay, cool. So this is the trick. So one pointer can point to two different things, right? Like essentially this mapping field when the page is like, for example, it's an anonymous page, which is either like was mapped through a map system call with like map shared and map anonymous fields. For example, when the process forks, this is how the data structures will look like. So essentially, you had your VM area struct, you had a pointer to your memory map struct, which contains a pointer to the page table, and like essentially the page table leads you to a page, right? When one process, for example, this one forks into a child, at this point they create this pointer they create a non-VMA area, right? And essentially now both of you, like you will create these links to the non-VMA area, and those will be maintained on a linked list, right? And essentially, like this is your parent and child, and this is eventually leads to the same page, right? And so essentially, this maintains a linked list of those anonymous, this linked list which I was mentioning here. And essentially, when you're saying, okay, I want to go through from a page, you go to your own virtual memory area and on VMA, and then you eventually even traverse this link and figure out who else is mapping the same page, right? Okay, that works. That trick works. And that's an okay trick, but it doesn't really work for reverse mapping file-backed areas. And the reason is the following. So some libraries like libc are literally mapped to almost every process in the system. It's very hard to build something without libc. I mean, it's possible if you really want, you can do it, but typically you don't do it. So typically you will have some libc, right? And so remember that here, when we go from a page to a linked list, then in order to figure out all the entries, all the mappings of this, like all the pages in which all the mappings of page table entries in which the page shows up, you traverse the linked list. So it's a little, like they say, it's too much for when the number of mappings is 5, right? And what they're doing instead, if they create something what is called a priority tree for every file in the system. So essentially, it's this IMAP field of the address space. Let me just show you. Remember that, like, if you go through those pointers to this data structure, which is called an address space, right? Then this one will have this IMAP field and will essentially lead you back here. And at a high level, what happens here is that IMAP field itself points to a tree. And this tree, I was talking about a different red leg tree. So this tree is called a priority search tree. And again, there is a paper which describes how this priority search tree works. And it's not exactly the same in a Linux kernel, but at a high level, it's a data structure which allows you to answer queries about intervals. Essentially, like whether you have a bunch of intervals, they may overlap, they sometimes show up multiple times. You ask a question, I have a sub-interval, in which intervals it shows up, and this data structure will answer it, right? Let me just explain why it's needed. So for example, here, like if you have a file, different processes might memory map different regions of the same file. So for example, here, a region from 7 to 12 is mapped by process 1. And here, the region, like whatever, this one is mapped by process 3. And this one is slightly, a sub-region within the first one is mapped by process 2. And essentially, imagine there is a page which is mapping this part. You have to answer, okay, which process maps it? And it's like 1 and 2, but not 3, for example, right? And this priority tree will answer you the question, right? And again, I will provide a link to the data structure, but at a high level, it's easier to understand through an example. So, although it's example, I quoted one book, right? So I quoted this Wolfgang Auer's book about the Linux kernel. There's another book which is called Understanding the Linux Kernel, and I will send a link to it as well. Again, sometimes one book is better than another, and in this specific example, this book is better. So it explains Wolfgang does not explain those priority trees, for example, or he does explain, but it's impossible to essentially understand what's going on. But what's going on here is like we have intervals ranging from 0 to 5. So for example, this one is encoded as starting as 0, size 5, and there is something what is called a heap of 5. And this is this interval, 0, 5, 5. The interval which is to the left of it should be like essentially shorter, and this is the one here, 0, 4, 4. The interval here is this one, it's a 2, 3, 5, right? And the point is that the sub-intervals, essentially like 0, 0, 0, this one is a subset, or not subset, but subset of 0, 4, 4, right? And so when you search, you essentially, for example, if you have a query asking which interval contains 5, you visit the tree, you say, look, this one clearly contains 5, so return this one. Then you visit the children, you send descended to 0, 0, 0, 4, 4, and you know that all of the other intervals do not escape this 0, 4, 4 range. And you say, okay, since this one is too small, then I don't have to explore the tree any further. However, for this one, you say, look, what about 2, 3, 5? Okay, this one contains 5. And then you still have to descend into these guys and figure out that they do not contain. And so essentially, you return interval number 1 and interval number 2 as a result of this query, right? Again, your algorithms class will probably explain that and send a link to the paper, but that's the idea. And so essentially, with this data structure, you can go from a page to everyone who maps a file or maps a page, who uses this page in a file-backed mapping. Okay, actually, this is the end of my wonderful lecture. So, any questions? So again, let me just quickly to reiterate what we learned. So the whole point was we started from the address space, right? And we said, okay, we're going to learn how to manage the address space, something like this. And I said, okay, we're going to support the following operations. We can quickly look up empty spots or gaps to figure out where we can allocate space. We do that with a linked list or a left tree. We can figure out exactly which address belongs to which, if you have an address, to which virtual memory area it belongs to a red left tree. This way we can do demand allocation or open right and stuff like that. And we figure out how to do the reverse mapping by essentially saying, I have a page which I try to take down to this, give me all the page table entries which map this page. And this is done for those either anonymous VMA regions which support copy and write and forking of processes, or this priority tree which goes through from a file, from file intervals, and answers you the question about who essentially maps those intervals. Good. So at this point, probably that's close to the last lecture on the virtual memory management. We will look at the forking, copy and write a little bit, and then move on to like other parts of the Linux kernel, but we'll spend a little bit more time doing the Linux kernel for the next couple of weeks. Okay, good. So one more announcement. So then office hours, let's quickly decide the time. For me, the most convenient time is before the class on either Monday or Wednesday, but will this time work for most people? Yes. So then let's do like an hour, let's say, yeah, something before the class on Monday to make sure that you can work on the homework. So, and the homework is, I don't know, you guys, I mean, okay, let me, since I still have a second.
You create Piazza?
I did create Piazza. It's accessible from the Canvas web page. Sorry, I forgot to send an announcement. Piazza is there. You can ask questions, but I wanted to see here. Let me just close. As I was digging through these books and everything, so I also found there is a guy who apparently just documents. I mean, there are multiple guys who document the Linux kernel, and it's pretty amazing actually. It's just, this guy works for Lenovo, Adrian Huang, apparently from Taiwan. And he has these amazing slide decks of like what's going on here. And it's again, it's something to be inspired by. So essentially, I discovered him too late to use his illustrations in my class. People want to do something this would be great. And the goal for this homework, again, just as an exercise to assemble some kind of a document similar to this, but with stack explaining how it works. So some people offer us to use it. So here, like again, like despite the fact that you have just listened to me, but you now understand what task struct is, and then pointer to the memory map, right? And then it goes to the list of virtual memory areas, which we present like different shared libraries and also the file data text and others. He just draws cute diagrams, but he also deserves a credit for things like this is the red black tree, which he explains quite well. But I wanted to show you his diagrams for he like apparently those slide decks are great. And he probably was, again, it was done in 2022, so like not too long ago. But for example, this is a slide for demand paging page fault. So if you ever want to, again, I kind of gave you a high level overview, but he probably did a way better job. So it's when you page fault, and a virtual memory area is anonymous page, so it's not backed by file. So it has this map private or map shared flag stat, and it's the first time access. So you don't find it, then okay, it's a sick fault, and then he lists specific functions, right? So this is handled and then fault, and he lists the version of the kernel for which he created the diagram. So I think it's version 5. It's the very first slide, right? But it's pretty cool, right? So you can, again, if we can do something similar to him, and I'm not saying, I mean, you don't have to do this, all of you can do independent diagrams with partial information, but then if we assign kind of editor-in-chief, we will publish on the class website with our own names. So it's not just Adrian, but all of us will be famous forever. But I mean, this, like, again, without those resources, and it took me a while how I landed on this slide deck by searching for a specific term, but it didn't even come to the slide decks before, so they are not easily discoverable. So this is 5.11, just like last year, I would say, or what is it, 2 years ago. Okay, that's pretty cool. Okay, so this is what I want you to do, an exercise in explaining the Linux kernel as a homework. But again, I will judge by, what is it called? By effort. So you can submit anything, just don't be embarrassing. But any answer is a good answer, but let's try to converge to something. Okay, cool. I'll stop here.